Hello. In this video, we are going to discuss and visualize the Langmuir isotherm using Lego brand locking bricks. To see the derivation of the Langmuir isotherm, you can take a look at this video. The first important variable in the Langmuir isotherm is M, and this is the number of absorbent sites available for our gas molecule to adsorb at. The variable capital N gives us the number of adsorbates. This is the number of gas molecules that adsorb onto the surface. The variable theta gives us the fraction of the available sites that are actually occupied by adsorbate molecules, and we can calculate this as M divided by N. The adsorbate molecules we are going to use for this demonstration is going to be carbon monoxide, which is an incredibly important gas in industry, which consists of carbon and oxygen held together by a triple bond. So this is the Lewis structure of carbon monoxide. Carbon monoxide has the interesting property that when it binds to a metal surface, it does so exclusively through the carbon. So let's just put Me here for metal. So it's going to bind to the metal, and it's going to bind at a 90-degree angle. So it's going to bind perfectly normal to the surface. Here is the model surface that we're going to use for the Langmuir isotherm. And we notice that we have 16 adsorbent sites, a 4x4 lattice. This would be typical, for example, for a simple cubic 100 surface. The gas molecule that we're going to use is carbon monoxide, which we have shown here at the bottom. The carbon atom is the black cylinder, and the red cylinder is oxygen. We note that when carbon monoxide binds to surfaces, it does so through the carbon atom, so we have to make sure that we put the carbon atom pressed down onto the absorbent site. So now that we have the carbon monoxide is now an absorbent rather than simply a gas. M choose N gives us the number of distinct ways of arranging our N adsorbate molecules on the M distinguishable sites, and we can calculate this as M factorial divided by N factorial times the quantity M minus N factorial. If we only have one adsorbate molecule, N equals 1, we know that M is equal to 16, so therefore we have 16 factorial divided by 1 factorial times 16 minus 1 factorial. 1 factorial is simply 1. 16 minus 1 gives us 15 factorial, so this becomes 16 factorial divided by 15 factorial. We can apply the fact that a factorial for 16 factorial is 16 times 15 times 14, all the way down to 1. So we can write 16 factorial as 16 times 15 factorial, since 15 factorial includes all the numbers multiplied from 15 down to 1. And then we notice that we have 15 factorial in both the numerator and denominator, so we can cancel these. And we get that the total number of combinations is going to be 16. It is one of the assumptions of the Langmuir isotherm that we only have monolayer absorption. What that means is we either have a site with nothing on it, as we see 15 of the sites here don't have a gas molecule adsorbed, or we have just one gas molecule. In the Langmuir isotherm, we will never have a situation we have, for example, two gas molecules on top of each other, or we have two different gas molecules, put the oxygen back there, that are both absorbed to the same site. So we either have 0 gas molecules per site or 1, and that's the maximum we can have. So in our model here, we have M being equal to 16. If N is equal to 1, we have 1 gas molecule adsorbed. So it is relatively straightforward to see that there are 16 different ways to do this because each of the sites is distinguishable and unique. So we could put it at the first site, this is the second site, third, and so on through all 16 possible sites. So we see clearly that our calculation that there are 16 ways to absorb one gas molecule, n equals 1, when m, the number of sites, is equal to 16. Now if we have two adsorbate molecules, n is equal to 2, the number of ways of arranging them is going to be 16 factorial divided by 2 factorial times the quantity 16 minus 2 factorial. 2 factorial is simply 2 times 1, or is equal to 2. 16 minus 2 is 14, so this gives us 16 factorial divided by 2 times 14 factorial. Again, using the properties of factorials, we can rewrite 16 factorial as 16 times 15 times 14 factorial. Our denominator is 2 times 14 factorial, so we notice that we can cancel 14 factorial from both numerator and denominator. Even more than that, we notice that we can cancel 2 into 16, which gives us 8. So with two adsorbate molecules on a lattice of 16 sites, we see that we have 120 different ways of arranging them. Next, we have the case where n is equal to 2, we have two adsorbate molecules. Our calculation had shown that there are 120 different ways to arrange these molecules. In the Langmuir isotherm, we assume that there are no adsorbate-adsorbate interactions. So therefore, there's no difference in energy between two adsorbate molecules absorbed right next to each other, as opposed to having them several sites apart. There are several ways to verify that our calculation of the number of different ways of arranging the adsorbate molecules is accurate. One way is just to systematically go through every possible combination and show that there are 120. But we can show a systematic mathematical method that's different than the approach we've already used that will confirm that, at least for the case where n is equal to 2, there actually are 120 different ways of doing it. We can proceed as follows. Let's set the first adsorbate molecule in the upper left-hand corner. Then we're going to systematically move the other adsorbate molecule through every other possible combination. So the first combination will be here, that's 1, 2, 3, and so on. And we notice that if we keep this one here and move the second one, there are 15 different ways to do that. So let's emphasize that number 15 because we're going to come back to it later. So now, let's set our first molecule to the second location. Now we want to make sure that we don't double count any permutation, any combination. So we're going to put the second adsorbate molecule, only the ones that come after this location. If we put this one back here, we would double count. So we're going to keep the second one, first spot would be here, second, third, fourth, fifth, sixth. And we notice that the second combination is going to be 14 different possibilities. So we started off, if we have this up here, it's going to be 15 possibilities. If we put it here, we're going to get 14 possibilities. Let's set it here. Now we notice we can put it at 1, 2, 3. If we go through all the possible locations that are after this location, and not putting any together, we notice now that we have 13 combinations. So we notice 15, 14, 13. Eventually we will get to a point where, at the end, we are going to only have one combination, and this is when we're at the last possible site. So we notice that we're counting 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So effectively, the number of permutations can be calculated by adding together all the numbers from 1 to 15. So in this case, using a small n, we would say that n is equal to 15. And we have a formula from mathematics that tells us if we add up the first n integers, the sum is going to be n plus 1 divided by 2. So that in this case, that would be 15 times 16 divided by 2, which turns out to be 120 combinations. So we verified both by working out all the possible permutations and by using another mathematical method to calculate that in this situation where we have 16 different sites, 2 adsorbate molecules, there are precisely 120 combinations. Now let's look at the case where n is equal to 3, we have 3 adsorbate molecules. So now the number of ways to arrange them is going to be 16 factorial divided by 3 factorial times the quantity 16 minus 3 factorial. Inside the parentheses, 16 minus 3 is simply 13, so this gives us 13 factorial. And then we realize that 3 factorial is 3 times 2 times 1, which is exactly equal to 6. So this now becomes 16 factorial divided by 6 times 13 factorial. We again apply the properties of factorials to write 16 factorial as 16 times 15 times 14 times 13 factorial, and our denominator is 6 times 13 factorial. And we notice first that we can cancel the 13 factorials from numerator and denominator. Next we notice that we can rewrite 6 as 3 times 2. So now we can cancel 3 into 15, which gives us 5. And 2 will go into 18, and we get an 8. Then we notice that 8 times 5 is 40, times 14 gives us 560. Different ways of arranging those 3 adsorbate molecules. Now suppose that n is equal to 3. So we have 3 adsorbate molecules on m equals 16 different adsorbate possible sites. So we see this is one possible combination. This is a second, a third. And we won't go through every possible combination, but realize that you could enumerate each and every one of these. And each one of these is distinct because each of the absorbent sites is unique. It's distinguishable from another one. It has a precise coordinate. It has a precise location in space. So this corner one is different than this one. It's different from the one next to it. So each is distinguishable. So we have to count each of those individually. I thank you very much for your attention. Stay safe. And as always, have a good one.